Now that we've covered the step input for a first order system, we've discovered that that gives you a fair bit of information, but it doesn't tell the whole picture. And so today, what we're going to talk about is a periodic input and the response that a first order system has for that. Since the step input is an oddly specific input and something you're not likely to encounter very frequently in nature, it's more useful to look at our sinusoidal input. And the reason for this is, if you recall from our discussion of a Fourier series, you can represent any signal as an infinite sum of sine waves. So if we have the frequency response of our particular first order system, which gives the amplitude and phase shift as a function of frequency, then basically we can solve any arbitrary response, the system's response to any arbitrary input, given the fact that the arbitrary input can be represented by a Fourier series. So we'll start with the governing equation. It's the same one as before. I will go ahead and leave the capital K in there for static sensitivity. In a lot of sources, you'll find that that is not included in this type of analysis, but we're going to leave it in there for now. The Laplace solution is the same as before, where we've got on the left-hand side or the leftmost term on the right-hand side is going to have the forcing component, and the rightmost term is the initial condition component. And in this case, we're going to let the forcing function be a periodic forcing function, a sine wave. And we're going to use complex exponentials here for simplicity. And I know you're probably thinking, simplicity? Complex numbers are never more simple. And I promise you, there are a number of reasons why they help out here compared to dealing with sines and cosines. So we're going to go ahead and say that f of t is equal to a times e to the j omega t. And that means that you can just look up in any standard table that the Laplace transform of that is going to be a over s minus jw. And recall that this is the same thing as a sine wave or a mixed sine and cosine wave, because e to the j omega t is equal to cosine omega t plus j sine omega t. Hopefully you remember that from pre-calculus or whichever class it is where they originally introduced that. So given this Laplace solution that we've just come up with, we can rearrange the terms a little bit so that now we have the leftmost term is Ka over 1 plus Ts times S minus Jw, and the rightmost term, the initial condition term, the transient term, remains essentially the same. So our goal then is to invert this. And what we'll do, and for reasons that will be apparent in a moment, we need to make sure that the two terms of the denominator of the left-hand side and the one term on the right-hand side, those are going to be s plus or minus something. We don't want it to be tau times s. We want to remove that tau. So on both sides then, we're going to take multiply the top and the bottom by 1 over tau. And so on the left-hand side, if we pull the two constants out and that new tau, that 1 over tau out, that gives us what we're looking for. And on the right-hand side, it's basically just going to cancel out the tau in the numerator. So that leaves us with two terms that we have to look up from a Laplace table. And so first we'll start with the right term because it's the easiest. That one is 1 over s plus 1 over t. And if we go and look it up in one of various tables on this topic, for example, the one that I uploaded to D2L, you'll see that 1 over s minus a is equal to e to the at. And here, a is going to be minus 1 over tau. And be very careful here with your signs, because this says s minus a, and we have s plus 1 over tau. So a is equal to minus 1 over tau. And so when you substitute that back in, inverting that Laplace transform, it results in e to the minus t over tau. The left term is a little bit more obnoxious, just because it's got extra pieces in the denominator. But it turns out that's also a standard form, and so we can look that up in the table as well. And we'll just note that a, in this case, is still minus 1 over tau, and then the b, in this case, is going to be j times omega. So if we substitute that into the inverse Laplace transform of this given by the table, we result in a 1 over tau plus j omega, and then you've got that times two different exponential pieces. And one of those is going to be a transient piece, and one of those is going to be something that's periodic and doesn't grow or decay. Finally, we're going to substitute that back into our equation for y of t that was in terms of Laplace transforms. And so we've got the ka over tau times that left term that we just solved, and the y naught times tau times the right term y naught times the right term that we just solved. And we can move the ka over tau into the curly braces there. So that gets rid of the curly braces. You've got ka over 1 plus j omega t, or j omega tau, I'm sorry. And then we'll note that we've now got two terms here that have e to the minus t over tau. So the next thing that we would conveniently like to do is to combine those terms. And so now, because those both represent transient effects, and the e to the j omega t is a steady state effect, we'd like to sequester those two terms separately. So now we split those apart. We've got a ka over 1 plus j omega tau times the periodic part, and we've got the y naught minus that same thing, ka over 1 plus j omega tau times the transient part. So this hopefully is starting to look a little familiar. We want to eliminate all of the j's from any denominators here. And this is basically the exact same process that we dealt with when we were talking about circuits, AC circuits. So 1 over 1 plus j omega tau, we multiply times, well, there's a typo here. It's supposed to be 1 minus j omega tau over 1 minus j omega tau, not 1 over. So I apologize for that. But we multiply by effectively 1, where 1 is made up by the complex conjugate over itself. And we can go ahead and use that to convert this into polar form, and we get the what hopefully is pretty familiar 1 over square root of 1 plus omega tau squared times e to the j phi, where phi is a phase shift term. So then in solution, we can substitute that in for those two like terms above, and we get something that is our steady state solution, which has the ka over square root term times an e to the j omega t plus phi. And then on the right hand side, even though we've got that phi term with a phase shift in there, ultimately that whole term is still multiplied times e to the minus t over tau, which goes to 0 as t goes to infinity. So the left hand term is going to be the steady term, the right hand term is going to be the transient term, and then that coefficient with the 1 over square root, hopefully that looks a little familiar to you. And I mentioned that before, but this should look awfully familiar because it's identical to what we calculated when we did the RC circuits back toward the beginning of the semester. Because RC circuits are a first order system. They're governed by a first order differential equation. We just came up with this and said that tau was equal to RC for that case. So this is the more generic way to arrive at that, and this is why I called that quantity RC tau back at the beginning of the semester, because it has a more fundamental meaning than simply what you would be able to take away from something as specific as a circuit analysis. So the next topic that we'll talk about here in the follow-up video is that term specifically that modifies the steady state solution to these kinds of problems.